Okay, so let's now look at acid base equilibria. Most reactions in chemistry occur in aqueous solutions. Okay, so most reactions occur in aqueous solutions that we know. Okay, so for example, the acid base reactions. You know that these normally you perform reactions in the lab, doing some titrations. Okay, so that occurs in aqueous solutions. We also have the buffered solutions. The buffered solutions, which contain components that enable the solution to resist a change in pH. Okay, so a buffer is able to resist a change in pH when hydroxide ions or protons are added. Okay, so hydroxide ions or protons are added. So OH, or the hydrogen ion, that is referred to as protons. Okay, so a buffering system or a buffered solution is able to resist change in its pH, pH. Okay, so we know that pH can be calculated in many ways. Okay, the one that is most famous is pH is equal to negative log hydrogen concentration. So we normally use this equation for a strong electrolyte. Okay, so buffered solutions are especially important in living systems, which can survive only in a relatively narrow pH range. Okay, so the most important, we know that the human body contains, or we can simply say the human body or blood, the human blood contains many buffering systems, but the most important of this is a mixture of carbonic. It's a mixture of carbonic acid, acid with a concentration of 0.0012 molar, and bicarbonate with a concentration of that's bicarbonate ion with a concentration of 0.024 molar. Okay, so these concentrations produce a pH of 7.4 for normal blood. 7.4 for normal blood. Okay, so because our cells, we know that our cells are so sensitive to pH, so it is important that this pH is maintained. For example, sometimes you may consume food, you may eat food that are acidic. Okay, so we do not expect this pH to drop. Okay, or sometimes you may eat foods that contains the bases that are alkaline in nature, so we do not expect this pH to increase. Okay, so the buffering system in the body is able to resist those changes when hydroxide or protons are added. Okay, though sometimes a change may be there, but it's minimal. Okay, so now let's look at solutions of acids. Solutions of acids or bases containing common ions. Solutions of acids or bases containing common ions. Solutions of acids or bases containing common ions. Okay, so suppose we have a weak acid. Suppose we have a weak acid. Suppose we have a weak acid, hydrofluoric acid. So this is hydrofluoric acid, which has Ka. It has Ka of 7.2 times 10 to the power negative 4. Okay, and its salt, sodium fluoride, and its salt, sodium fluoride. Okay, so we have the weak acid HF and its salt, sodium fluoride. Okay, so when the salt, this is a strong electrolyte. Okay, so when this salt dissolves in water, it breaks up completely into its ions. So we can see sodium fluoride will form sodium ion plus fluoride ion. Okay, so this one is a strong electrolyte. Okay, it completely ionizes in solution. Okay, so now when we mix the solution of sodium fluoride and the acid, we know that the acid, though it's a weak acid, it will also ionize in solution to form. So hydrofluoric acid will ionize or dissociate in water to form hydrogen ion plus fluoride ion. Okay, so these two are in one vessel. So now you can see that there is a fluoride ion which comes from the salt. There's also a fluoride ion that comes from the acid. So this is a common ion since it is produced by both the acid and the salt. Okay, so now according to Le Chatelier's principle, since more fluoride ions are being produced, these when we add, there's fluoride ion from the acid and from the salt, so there'll be more fluoride ion in the vessel. So in this case, the equilibrium will shift to the left. The equilibrium will shift to the left. Okay, so we know that we use Le Chatelier's principle. Le Chatelier's principle. Okay, so the shift in equilibrium position, position that occurs because of the addition of an ion already involved in equilibrium reaction is what we call common ion effect. Common ion effect. Okay, so this effect makes a solution of sodium fluoride plus hydrofluoric acid less acidic than a solution of hydrofluoric acid alone. Okay, so now we have seen that when you introduce the salt into this acid, then the acid dissociation, the extent of dissociation of the acid will be greatly reduced by the presence of the common ion. As a result, this solution will become less acidic than a solution of hydrofluoric acid alone. Okay, so that is the effect of this common ion. Okay, so it will make the equilibrium will shift away from the added component, since more fluoride ions will be produced. So the equilibrium now will shifts to the left. Okay, to balance up the fluoride. Okay, so now the common ion is quite general. For example, we can also look at ammonium chloride. For example, ammonium chloride added to a 1.0 molar ammonia solution. 1.0 molar ammonia solution produces additional ammonium ions. Okay, so this one can dissociate as follows: ammonium chloride, then plus water, so it will give us ammonium ion plus chloride ions. Okay, and this causes the position of the ammonia water equilibrium to shift to the left. Okay, so ammonia, then plus water, then will give us ammonium ion plus ammonium ion plus hydroxide ion. Okay, plus hydroxide ion. So in this case, the equilibrium will shifts to the left. Equilibrium shifts to the left. Okay, so this reduces the equilibrium concentration. This reduces the equilibrium. It reduces the equilibrium concentration of hydroxide ions. Okay, so the common ion effect is also important in solutions of polyprotic acids. Okay, so the production of protons by dissociation steps, by the first dissociation step, greatly inhibits the succeeding dissociation steps, which of course also produce protons, the common ion in this case. Okay, the protons, the common ion in this case. Okay, so having done that, let's look at some equilibrium calculations. Equilibrium calculations. So example. So in this example, we shall look at acidic solution containing a common ion. Okay, so the equilibrium concentration of hydrogen ion, in a 1.0 molar hydrofluoric acid solution. Hydrofluoric acid solution is 0.032 molar. And the percent dissociation of hydrofluoric acid, is 3.2 percent. Then calculate the concentration of hydrogen ion and the percent dissociation of hydrofluoric acid in a solution containing 1.0 molar hydrofluoric acid 1.0 molar hydrofluoric acid. We know Ka is equal to 7.2 times 10 to the power negative 4, and 1.0 molar, and 1.0 molar, and 1.0 molar sodium fluoride. Okay, so what we need to look at here, we want to compare the percent dissociation. So the percent dissociation for hydrofluoric acid, when it is alone, it is 3.2. Okay, so now let's calculate the percent dissociation when it is now mixed with sodium fluoride. It's salt. Okay, so to solve this question, okay, we can also look at the major species in solution when the two are mixed. Okay, so the major species in solution when hydrogen fluoride, when hydrofluoric acid and sodium fluoride are mixed. So the major species in solution is hydrofluoric acid, fluoride ion. We have also sodium ion, and water. So these are the major species. So this one is a weak acid. It partially dissociates in solution. Okay, so now we know that this one, the sodium ions have neither acidic nor basic properties. They have neither acidic nor basic properties. Then water is a very weak acid, very weak acid. Water is a very weak acid or base. Okay, so these two do not participate in the dissociation, in the acid dissociation equilibrium. Okay, so now what participates is simply these two. That's what controls the concentration, the acid dissociation equilibrium. Okay, so we rule out the sodium and sodium ion and water. Okay, so we are going to use the ICE table. So we write the equation. Sodium hydrofluoric acid then forms hydrogen ion plus fluoride ion. Okay, so this is the equation. Okay, so we write ICE. Okay, so the initial concentration of the acid, is 1.0 molar. Then the initial concentration of the hydrogen, that is 0. Then the initial concentration of fluoride ion, that is also 1.0 molar. The fluoride ion that comes from the added sodium fluoride. Okay, so change will be minus x plus x plus x. Okay, then equilibrium 1.0 minus x 1.0 minus plus x. Okay, so this is the table. That is how the table will look like. Then now we write the Ka expression. Ka expression. So we know that Ka will equal to concentration of hydrogen ion. Concentration of hydrogen ion times concentration of fluoride ion over concentration of the acid. Over concentration of the acid, which is given as which is equal to 7.2 times 10 to the power negative 4. That is the Ka given. Okay, then now we substitute the equilibrium concentrations into the expression. So we have 7.2 times 10 to the power negative 4 is equal to hydrogen concentration, which is X, then fluoride concentration, that is 1.0 plus X, then over concentration of the acid, which is 1.0 minus X, 1.0 minus X. Okay, so to solve for X, we need now to solve for X. So to solve for X, we are now going to use some assumptions, what we call the 5% rule. Okay, so we assume that X is so small. X is so small compared to 1.0. So therefore we neglect X. And the assumption is valid by 5% rule. Okay, so if X is neglected, this equation will be 7.2 times 10 to the power negative 4, which is equal to X. Then it will be 1.0 over 1.0. So you can see that the 1.0 will cancel out. So we can safely say X is equal to 7.2 times 10 to the power negative 4. Okay, so approximations are valid by 5% rule. 5% rule. Okay, approximations are valid by 5% rule. 5% rule. Okay, so if X is equal to that is the concentration of hydrogen. Okay, so we know that concentration of hydrogen is equal to X, and our X has been given there. So which is equal to 7.2 times 10 to the power negative 4 molar. Okay, so this is the concentration of X. So if you know the concentration of X, you can as well calculate the pH. We know that pH is equal to negative log hydrogen concentration. So negative log 7.2 times 10 to the power negative 4 will give us it's going to give us so you can do some calculations there. So the pH, when you calculate, it will give you 3.114. So that is the pH. That is the pH of the solution. So we have calculated the concentration of hydrogen. So now what we need is the percent dissociation. So let's calculate now the percent dissociation. So we keep in mind the concentration of hydrogen because we shall use it. So we'll write it here. Concentration of hydrogen 7.2 times 10 to the power negative 4 molar. Okay, so now let's calculate the percent dissociation. We can now calculate the percent dissociation. Okay, so percent dissociation is given by hydrogen ion equilibrium concentration over initial concentration of the acid, then times 100%. Okay, so now we simply substitute there, which is straightforward. So the equilibrium concentration of hydrogen is what we have calculated, which is 7.2 times 10 to the power negative 4 molar, then over initial concentration of the acid is given there, 1.0 molar, 1.0 molar, then times 100 percent, of which when we divide we are going to get 0.072%. Okay, so this is the percent dissociation in the presence of the common ion. So you have seen that the percent dissociation has greatly reduced. When the acid was alone, the percent dissociation was 3.2%. But once the common ion was introduced, it has greatly reduced. So we can conclude that the common ion inhibits the acid dissociation. Inhibits the acid dissociation. Okay, so that is how we can calculate. So we can also look at some factors affecting percent dissociation. Factors affecting percent dissociation. Factors affecting percent dissociation. Factors affecting percent dissociation. So number one is concentration. Okay, so as a weak acid solution, becomes more diluted, the percent dissociation increases. The percent dissociation increases. Percent dissociation increases. Okay, then number two, we have also Ka value, the Ka value. Okay, so a larger Ka value indicate a stronger weak acid. And the results in higher percent dissociation. Okay, higher percent dissociation. Okay, so these are some of the factors that affect percent dissociation. Okay, another example. We are still calculating percent dissociation. Okay, so for a 0.100 molar solution of a weak acid, with a 1.33 times 10 to the power negative 3 molar concentration of hydrogen ion at equilibrium. Calculate the percent dissociation. So solution, we know that percent dissociation. So this is the equation for a 0.100 molar solution of a weak acid with a 1.33 times 10 to the power negative 3 molar concentration of hydrogen ion at equilibrium. So calculate the percent dissociation. So we apply the formula percent dissociation, which is equal to hydrogen ion concentration over acid, then times 100. Okay, so the equilibrium concentration of hydrogen, it's given 1.33 times 10 to the power negative 3 molar. Then concentration of the initial concentration of the acid, that is 0.100 molar. Okay, then now you divide and multiply, then you are going to find 1.33%. Okay, so as you can see, the percent dissociation is less than 5%. So it means our assumptions are valid. Okay, they are valid. So percent dissociation of a weak acid measures the fraction. Percent dissociation of a weak acid measures the fraction. The fraction of acid. The fraction of acid molecules measures the fraction of acid molecules that ionize in water. Usually resulting in low percentages, as we have seen, in low percentages, less than 5%, for weak acids. Okay, for weak acids. So that is how we can define or explain percent dissociation. Okay, so now we can now look at buffered solutions, or we shall look at buffered solutions in the next lecture. Okay, so the next one we shall look at buffered solutions.